Greetings and welcome to our 112th test and measurement video. Today we'll do an overview of the math mode in the Tektronix MDO3000 oscilloscope. To obtain signals for this demonstration, I have connected via BNC cables channels 1 and 2 in the arbitrary function generator to channels 1 and 2 in the oscilloscope. All channels have to be on. And the AFG placed in the basic mode so that signals can be accessed from its internal library of waveforms. As you can see, currently sine waves are being generated in both AFG channels, and they are being displayed in the oscilloscope. The Tektronix AFG has a touch screen, and it is a simple matter to activate the appropriate drop-down menu in either of the channels. We see the list of waveforms, and they can be displayed individually in channel 1 in both instruments. The available waveforms are sine, square, ramp, pulse, noise, sine x over x, DC, Gaussian, Lorentz, exponential rise, exponential decay, and Haversine. To get good displays, some of the waves have to have auto set pressed. The same waveforms can be displayed in both channels. Notice also in this same screen, waveform parameters can be set separately in each channel. For example, right now, the default frequency is 1 megahertz. Amplitude is 1 volt peak to peak. Phase difference is 0 degrees, and offset is 0 millivolts. We'll look at the sine waves with the oscilloscope placed in the math mode. To begin, press the red math button on the oscilloscope front panel. The horizontal math menu appears below the display. Notice that the waveforms as shown in the oscilloscope are yellow for channel 1 and blue for channel 2. These are the two dedicated colors for the oscilloscope channels. The red waveform is the result of various math operations. The default math mode is dual waveform math. Pressing the associated soft key, the vertical dual waveform menu bar appears at the right. Default parameters are automatically entered. The first source is channel 1 and the second source is channel 2. The operator is plus, denoting addition. Any two waveforms can be added, even if they are totally different types. They are added on a point-by-point instantaneous basis. Notice here that when the peaks of both go high, their sum goes high, and when the peaks go low in a negative direction, the sums in red go twice as low in a negative direction. When the sources go to 0, as when they cross the x-axis, as at the left edge of the display, the sum is 0. Using the soft key associated with multiply in the operator menu, the red math trace shows the instantaneous product of the two sources. Divide is a little baffling until you recall that you can't divide by zero, as illustrated by those red peaks that are trying to reach for infinity. Returning to the horizontal math menu, we'll press FFT and see what the sine wave looks like in the frequency domain. Removing the menus, we can get a good look at it. The fundamental is at the left of the display, and you can see that is where all the power is. There are no harmonics. The irregular fluctuating line represents the noise floor of the instrument. Doing the fast Fourier transform, only one source is required. Using multipurpose knob A, you can make two the source, but the frequency domain representation looks the same, since the waves displayed in the time domain are the same in both channels. Going back to the drop-down menu in the AFG, we'll send over to the oscilloscope a square wave. Notice how different it looks in the frequency domain. As opposed to the sine wave, there is less power in the fundamental. The power is distributed in the harmonics, which diminish in amplitude as spectral distance from the fundamental increases. The final mode in the horizontal math menu is Advanced Math, which will be the subject in video 113. Thanks for watching. New videos are added periodically, so check back frequently.